Let's study various topics in fluid statics. Fluid statics. So in fluid statics, there is no flow in the fluid and external forces are also not there. The only external force that we consider in the fluid is the gravitational force. So in the fluid statics, the various topics that we'll cover is: number one, the pressure distribution in the fluid. In this, we'll study about the Pascal's law, the hydrostatic pressure. Next, we'll study the force on the submerged bodies. Because of the fluid. So let's start by studying the Pascal's law first. So Pascal's law states that the pressure at any point in the fluid is same in all directions. That is, let's say if you have a point volume element, let's say, and this is, let's say, my fluid, and this is my tiny fluid element, then the pressure from this direction, 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 this direction, this direction, this direction, or this direction, the magnitude of all these pressure values would be, all these pressures would be same. So let's derive the Pascal's law by considering a wedge-shaped fluid element. So let's consider this wedge-shaped fluid element with coordinate axes x, y, and z. Let's say the edge along x-axis is delta x, the length along y-axis is delta y, and the length along z-axis is delta z. Okay, for better understanding, let's study this problem in 2D. So let's say I am looking the wedge from here, somewhere from minus y-axis, and for that observer this would look like this. So this is a wedge, this is x-axis, this is z-axis, and into the board it is y-axis. Okay, this length is delta x, this length is delta z, and let this be delta s. Let the wedge angle be theta and gravity acting downwards, that is in the minus z direction. Now let's say other fluid molecules or other fluid particles are applying pressure on this fluid element, and the pressure is given by the following. So this pressure is, since it is in z-axis, so let's say Pz, the pressure on this surface be Px, since it is along x-axis, and the pressure on this surface be Pn. And let the pressures along y-axis, let's say this is Py1 and let's say this is Py2. Okay, now if this fluid element, this wedge-shaped fluid element is in equilibrium, this would mean that all the forces should cancel out each other, right? That is, summation of all the forces along x-axis should be 0, summation of all the forces along y-axis should be 0, and summation of all the forces along z-axis should be 0, right? Now to understand force due to pressures, first let's resolve this Pn into two components, one along z-axis and the other along x-axis. So if this is theta, you can use simple angle laws to find that this should also be theta. So this would be Pn cos theta and this would be Pn sin theta. Now on this fluid element, what are all the forces that is acting along x-axis, that is along this axis? So this is your x-axis. What are all the forces that is acting on this fluid element? The answer is, the one force is because of this px and the other force is because of this Pn sin theta. That's it, right? So if we, for summation fx to be 0, we should have px, the magnitude of px should be equal to the magnitude of Pn sin theta, right? Similarly, for summation fy to be equal to 0, since only py1 and py2 are the pressures, okay, so force will be converted to pressure by multiplying pressure with area. So this would be the area. So px is acting on this surface, right? So we have to also multiply the area as well with the pressure px. So what is the area of this surface? What is the area of this part? So this is simply delta y times delta z. So you have to also multiply delta y times delta z with this. And Pn sin theta is acting on this surface. Okay. So what is the area of this surface? So this is delta s and this is delta y. So the area would be delta s times delta y. Similarly, summation for summation fy to be 0, we should have py1 times this area equal to py2 times this area, and since this area and this area is equal, we'll simply get py1 equal to py2, right? And for summation fz to be equal to 0, now what are all the forces that are acting on this fluid element along z-axis? So one is this pz times the area of this part, then there is this Pn cos theta which is acting on this surface in the minus z direction, and also because of this weight of the fluid element, the force due to gravity is acting along minus z direction. Okay, so there are three forces. So let's write them. So the one is pz times the area of this part. Now what is the area of this part? The area of this part is delta x times delta y. Just write it down, delta x times delta y, acting along, so this is acting along positive z direction, right? Okay, and the other forces are acting along minus z direction, so this should be equal to the magnitude of the forces acting along minus z direction. Okay, so what are the one force acting along minus z direction is Pn cos theta times the area of this part. So this should be equal to Pn cos theta times the area of this part. So what is the area of this part? We already find the area of this part, delta s times delta y. Just multiply delta s times delta y plus weight of this fluid element. Now let's say if rho is the density of this fluid element, then what would be the weight of this fluid element? It would be density. So what is the weight? Mg. So we can write m in terms of we can write m equal to rho v. So rho is the density, v is, let's say, the volume of this fluid element, let's say v, and times gravity. Okay, so this will be the force due to gravity on this fluid element along z direction. But we can also write volume in terms of delta x, delta y and delta z. So what will be the volume of this wedge shaped element? The volume will be simply the area of this portion times the length. Okay, so what is the area of this triangle? The area of this triangle is half base times length. So that is rho g. Now half base is delta x, length base times height is delta z, and so this is the area. Now we have to multiply this with this depth, which is simply delta y. So just multiply delta y. So this is your force value. Now this can be further simplified, since delta y and delta y would cancel out. And also you can see from this figure, so let's just make this figure again, and this is your delta s, this is your theta. So what is delta s cos theta? So this is delta s cos theta, which is equal to delta x, and this is delta s sin theta, which is equal to delta z. So we have delta s sin theta term here, this is equal to delta z, so this and this can cancel out. So what we'll get is, we'll get px is equal to pn. This we have already got. Next, let's try to simplify this expression. So delta y and delta y would cancel out, and delta s cos theta, this cos theta times delta s, this is equal to delta x. So this can be simplified to, let's say, delta x, and since we have delta x here and here, so this gets cancelled out, delta x. So what we are left with, so this expression now we are writing again. So this can be simplified to pz equal to pn plus half rho g times delta z, right? Now since in the fluids, since here we wanted to understand that for a point fluid element, whether the pressure acting along all directions is same or not. So for a point fluid element, this delta z will approach to 0. So this expression would become pz equal to pn plus 0, which is simply pz equal to pn. So what we got from here, the first thing that we got from here is px equal to pn, second thing py1 equal to py2, and the third thing is pz equal to pn. So from here we can understand that the pressure acting along all directions for a point fluid element are same, since we just derived that the pressures which was acting along some different directions, let's say px, pz, pn, they all were found to be same. So this is what Pascal law states, right? So we just derived the Pascal's law for our static fluid element. Next, let's understand the pressure variations in the fluid as a function of the various directions, let's say as a function of height, as a function of length, as a function of breadth of the fluid. So let's consider a cubical fluid element. Coordinate axis x, y and z. Again, let's say the length along the y axis is delta y, the length along this is delta x, along the x axis is delta x, and the length along z axis is delta z. Okay, so and this fluid element is infinite small, so delta x, delta y and delta z all are approaching 0. So if this point, let's say like an origin, then this would be my x-axis, this would be my y-axis, and this would be my z-axis. Okay, now we want to study what are the forces, or what is the force that is generated because of the pressure variations in along these axes. So the force because of the pressure variations along, let's say, y-axis, let's say this pressure is, so at y plus delta y, this pressure is P of y plus delta y, and this pressure is P of y. Then the force along the y-axis dFy will be given by P of y plus delta y times the area, which is delta x times delta z, minus P of y times the area delta x times delta z. So we can just take delta x into delta z outside. So this would be the force on this fluid element along y-axis, right? Similarly, we can write the force in the z-axis dfz, that would be equal to P of z plus delta z minus P of z times the area, which is this area. Now what is this area? This area is delta x times delta y, delta x times delta y, and similarly dfx will be P of z plus delta z, P of x plus delta x minus P of x times delta y delta z. Okay, now to expand this P of y plus delta y in terms of P of y, or P of z plus delta in terms of pz, or Px plus delta x in terms of Px, we will use Taylor's series in mathematics. So what Taylor's series tells me, it tells me that a function x plus delta x, if delta x approaches to 0, this can be written in terms of the partial derivatives of f of x, that is f of x plus del f upon del x into delta x plus half del square f upon del x square into del x whole square plus 1. Now we assume that the higher orders can be neglected for our problem, and we'll only take the first two terms in the Taylor series. So now I can write for dfy, this would be P of y plus del p over del y minus P of y into del x del z, right? P of y would cancel out with P of y, and I'll be left with del p by del y, del x del y del z dfy. Okay, note that there is a sign mistake in this derivation. So if you think carefully, then d of fy is actually the force acting along the positive y direction, right? And P of y plus delta y is directed towards minus y axis, and P of y is directed along positive y axis. So d of fy should be given by P of y minus P of y plus delta y, and similarly dfz should be given by this, dfx should be given by this, and thus d of fy, this would look like this, and here you will get minus del p over del y into del x del y del z. So is it clear that there was a sign mistake done by me? Okay, now similarly For other directions, we'll get dfx equal to minus over del p by del x into del x del y del z, and dfz is equal to minus over del p by del z into del x del y and del z. Okay. So the total force df vector would be dfx I hat plus d, so dfy j hat plus dfz k hat, with I hat is a unit normal along x-axis, y hat along j hat along y-axis, and k hat along z-axis. Okay. So using the previous expressions, we can write minus over del p by del x I hat plus del p over del y j hat, sorry, there would be a negative sign here, minus del p over del z k hat times del x del y and del z. Now we can further simplify this by writing minus over del by del x I hat plus del over del y j hat, or better just write it like I hat plus j hat del over del y plus k hat del over del z times p and del x del y del z. So this can be written, so in mathematics this is denoted by grade vector. So this will become minus over grade p times the volume del x del y del z of the fluid element. So this df is given by this expression. Okay. Or we can also define small f vector, which is force per unit volume of fluid element. So this expression would become d small f vector equal to minus grade p. Okay. So this expression means that if there is a pressure gradient in your fluid element, then that pressure gradient would generate a force per unit volume on the fluid element. Okay. This F is actually differential of force per unit volume. So actually dF by delta volume. So then we just write this as the force due to differential force per unit volume due to the pressure variation is given by minus over grade P. So now if the fluid element is static, then the force per unit volume due to the pressure variation plus force due to gravity due to the weight of the fluid element should combine to give you 0, right? So Fp is given a minus 4 grade P plus, now given the axis in the problem, the gravity is acting in the minus z direction. So then this Fg will be given by the density. Okay, so this is actually the force per unit volume, so that's why it will be simply written by rho times g vector equal to 0 vector, grade P will be equal to rho times g vector, right? Now writing this expression in terms of different coordinate axes, we'll get grade P in the x-axis should be equal to rho g in the x-axis, grade P in the y-axis should be equal to rho g in y-axis, and grade P in z direction should be equal to rho g in z direction. Okay. Now this g is not along x and g is not along y, So the component of G along x-axis is 0. So this expression would become 0. Similarly, the component along the y-axis is 0. So this would become 0. And component of G along z-axis is actually minus G vector. So this would become minus rho G. Okay. So this tells me, this expression tells me that del P, if I just write gradient in x direction, that will be, so what was gradient? Gradient was I hat del by del x plus j hat del by del y plus k hat del by del z. So what is the gradient along x axis? That is simply del by del x. So this will become del p by del x. So del p by del x is equal to 0. This gives me del p by del y equal to 0, and this gives me del p by del z. Okay. So these three expressions tell me that pressure is only along, or is pressure is only a function of z, right? So then we can write del p by del x as dp by dx, del p by del y as dp by dy, and del p by del z as dp by dz. Okay. And this is equal to 0, this is equal to 0, and this is equal to minus rho g. So this tells me that pressure, so if I only have a static fluid and that is only being acted by the gravity, then pressure is not a function of x, pressure is not a function of y, but pressure is just a function of z. So what do we imply from here? That if you have a cubical fluid element, then this pressure value and this pressure value is equal, this pressure value and this pressure value is equal, and this pressure value and this pressure value has a relationship which is given by this expression. Okay. So let's try to simplify this expression. So this equation will be now be written like dp by dz equal to minus rho g. This thing implies dp is equal to minus rho g dz, so let's again just write it, dp is equal to minus rho g dz. Now if I integrate along from z equal to z1 to z equal to z2, and let the pressure values from at z equal to z1 be p1 and z equal to z2 equal to p2, not pz, but let p2, then I can get an expression of p as a function of z. Okay. Now this expression can be broken for liquids and for gases. Can be done for liquids and for gases. So let's first do for liquids. Okay. Now for liquids, density, so for liquids density does not change as a function of pressure, so we can take density outside of this integral, and also the length values, the z height values z1 z2 that we are studying is not very large, so that the gravity would change. So that's why we can take g outside of the integral as well. So this p1, integral p1 to p2 dp, what would it become? It will become p2 minus 4 p1, and this expression would become minus rho g integral dz from z1 to z2, which can also be written like minus rho g z2 minus z1. Okay. So what does this expression mean? So let's say if you have a liquid in some container, let's say it is filled till some height h. Let's not take this height h. So we want to see what is the pressure variation along z axis for, let's say, 2 points. So let's say this is A and this is B, and we want to see what is the pressure difference at these 2 points. So from this expression we would see that P2, which was at higher z, so this would be PA, and P1, which is at lower z, which is PB, will be equal to minus rho g times Z2. So Z2 is at higher, so this is Z of A minus Z1, which is Z of B. Okay, or we can write PB minus PA equal to rho g times ZB minus ZA. And let's say this ZB minus ZA since negative sign I have sent here, this will again be ZA minus ZB. And now let's say this A, or before that let's try to understand this expression. So this tells you that when you go deeper and deeper inside the fluid, the pressure will increase. Okay, now let's assume that this A is actually on the free surface. So let's say this A is on the free surface and B, okay, so let's again just change the figure a bit. So this is your fluid, in some vessel. Now A is here and B is at some depth h. So just like that we can write PB minus PA equal to rho GH, right? And since this PA is the free surface, so we denote free surface from this inverted triangle. So what would be the pressure of A? This would be simply atmospheric pressure. This will be equal to rho GH, or PB is equal to P atmosphere or PB is equal to P atmosphere plus rho GH. So this is called fundamental equation of hydrostatics. So this expression tells me that if I have, let's say I have a volume element in my fluid, then the pressure at this one would be, if the pressure here is P atmosphere, then the pressure here would be P atmospheric plus rho GH. That is, the pressure here would be equal to, first of all, the atmospheric pressure, and also this extra term is there because of the volume of this fluid element that it has to balance. Okay, so there is a pressure from the atmosphere plus there is a pressure from the weight of this fluid element just above this point. So the pressure here has to balance both those forces, and that's why the pressure here is P atmospheric plus rho GH. Okay, let's do similar analysis for gases. So first let's take this expression. So we have this expression. Okay, so it's better not to write integrals currently. because rho would be a function of pressure in case of the gases. How would that be? We'll use the ideal gas law to get that expression. So from ideal gas law we know that PV is equal to nRT, or P is equal to N by VRT, or number of moles can be given by given mass upon molecular mass times VRT, and this M by V is nothing but the density rho RT by MW. And for different gases we know the value of R by MW. We also write this as the specific gas constant. The same as this P will become rho Rg times T. So we'll just plug in this expression for density P by rho P by Rg times T. So this would become dP is equal to minus P by Rg times T into G into dz. So plugging in P there, dP by P is equal to minus of G dz upon Rg T. Now integrating both sides from Z1 to Z2, we get ln of P from P1 to P2 is equal to minus over G by Rgt. So again we are assuming that G, Rg and T will be independent of Z, and that's why they can be taken outside of the integral, and this would become Z2 minus Z1. So this would become ln of P2 by P1 is equal to minus over G Rgt times Z2 minus Z1. Now let's say this is our Earth's surface and we want to find, and this is P atmospheric at this Z equal to 0, and we want to find the pressure value with respect to height h. Okay, so then this Z1 would become 0, Z2 would become h ln P by P atmospheric equal to minus over G by Rgt. Z2 would become h and Z1 become 0. So this would become P is equal to P atmospheric e to the power minus G h upon Rgt. So this is the formula for a gas, the pressure distribution in a gas as a function of the height. Okay, and the pressure value here would be greater than the pressure value at here by this factor, by the factor of P atmospheric minus P atmospheric e to the minus over Gh upon Rgt. Okay, so as you go above the surface, the pressure of the air would go on decreasing. Okay.